So this is part 2 of alkyne reactions. I'd like to begin with a very simple reaction of just an addition reaction with hydrogen. This would be a reduction, most commonly known as a hydrogenation reaction. We'll be adding 2 parts of hydrogen gas along with a metal catalyst. You can use platinum, palladium, or nickel. This will reduce to the alkene and continue to reduce all the way to the alkane. So notice here we have no hydrogens on our alkyne. And in the product with the alkane, we have 4 hydrogens. This will have full alkane conversion. Now, what if we want to do a reduction where we start with an alkyne but stop at the alkene? Well, there's 2 common ways to do this. We can use Lindlar's catalyst. This will give us a cis alkene, or we could use a metal ammonia reaction where we'll get a trans alkene. So let's take a look at both of those. So at the top there's Lindlar's catalyst. This has all of these ingredients where you'll have hydrogen gas along with barium sulfate. This barium sulfate, I have a note here, is coated with palladium as well as quinoline, which is this structure here, which has 2 aromatic rings with a nitrogen fused inside one of the rings. This is all in methanol, and you'll notice that we'll get our 2 alkyl groups pointing in the same direction for a cis geometry. The other type of reaction is metal ammonia. The metal will be sodium, and this is ammonia. This will go through a very interesting reaction that is a radical cation reaction, and we'll get a trans geometry. You could research the mechanisms a little bit more if you're interested, but I just wanted to give you the general reactions of those to show you how you could stop at the alkene and the geometry specificity between these 2. Another type of addition reaction to alkynes will be just addition of halides. So we could add 1 equivalent of our halide and we'll stop at the alkene. This will also give us some preference. Usually you're going to get more of the trans. It's in 75% roughly, and the cis, where the R groups are on the same side, will be about 25%. You will get a mixture, so there will be a little bit of separation techniques you'll need to perform. If you add 2 equivalences of the halide, you'll actually get side-by-side vicinal examples as shown here. I didn't mean to put that line through it, but you can see what I mean. The next type of reaction is addition of hydrohalic acids, just your normal hydrochloric, hydrobromic, or hydroiodic acid, as shown here. Here's a hydrogen attached to any halogen. And I should have mentioned in the last slide, X represents any of the halogens. So here we have an alkyne. This one is a terminal alkyne because of this hydrogen that's present. Notice here we'll get conversion to the alkene. The hydrogen is going to add to the carbon that has more hydrogen, so this is a Markovnikov type process. This will continue all the way to the alkane. I'll show the mechanism below, and we will get a vicinal dihalide. So taking a look at the mechanism, we're going to have a nucleophilic attack here. We'll pick up the proton, send off the halogen leaving group. Hydrogen goes to the less substituted side. So that will be Markovnikov addition. We produce a carbocation. The carbocation needs to go to the side that's more substituted so that it will be stabilized, because this R group will donate a little bit of electron density. The halide that we just bumped off can now come in and attack the empty orbital here with our positive charge. So you can see now we've added our halogen. This will react again if we have enough of the hydrohalic acid present. So here's a second reaction. Send off the halide. This will be Markovnikov addition once again. So you can see the hydrogen added to the side that has 2 hydrogens. We form our carbocation. This will be an attractive force for the halide to attack, and we get our dihalide product. The next type of reaction I'd like to go through is a hydration reaction. This is going to be with water as well as a mercury sulfate complex along with sulfuric acid. This gives us something that we haven't seen before, where we'll have a carbonyl next to an alcohol. I have it outlined here. This is called an enol. It's like we've combined the terms alkene and alcohol together to get enol. These are not very stable because we have these pi electrons right beside the lone pairs of electrons on the oxygen. So there's going to be a more stable form of this once it isomerizes or changes its arrangement to this ketone. It goes through this process called a tautomerization, and it's a keto-enol tautomerization. It's kind of a mouthful to say. We're going to show this hydrogen moving from the alcohol where it's attached to the oxygen to all the way over to this other carbon, and the oxygen will now be double bound in the end. So let's take a look at the mechanism of how this occurs. There's two ways that we can have a tautomerization. One of those will be in acid, and the other one will be in base. In the case of the reaction that we just looked at with the hydration, this will be an acidic tautomerization. So we're going to take our enol, and we're going to use the alkene portion of it, and it's going to react with the acid, so we get a deprotonation of the acid. This will put the hydrogen on the carbon with more hydrogens on it, the less substituted carbon. So this is like a Markovnikov type process. We get our carbocation on the carbon that has the alcohol. I have the lone pairs on the alcohol labeled in red. These can resonate. Notice our arrow here. This is resonance arrow. The only arrow that will be used with heads on either side of it is resonance, and that's just movement of electrons. So this process right here between these two show the movement of electrons, whereas the enol to the ketone shows the movement of an atom. So we have movement of an atom and resonance within. So just make sure you know the difference between resonance and the tautomerization. So resonance is within this process, so just the movement of electrons. We form a stabilized carbocation, so we can move it from the carbon to the oxygen by donating electron density down to it. Water, we have water because we just deprotonated acid. Water can come and pull off this proton, and then we get our ketone. The enol and the ketone are in equilibrium with each other, but the side is going to favor the production of our ketone. Here's an example reaction. I have a terminal alkyne, and this is just to show just the general reaction of it with the reagents listed. So here's our water for hydration, the mercury sulfate, sulfuric acid. This forms the enol, and then in the presence of the acid we get our tautomerization to our ketone. The next type of reaction I would like to go through also goes through a keto-enol tautomerization, but this time it'll be base catalyzed. You'll get to look at the opposite. This is going to be a hydroboration oxidation. It's anti-Markovnikov. I have that noted. It uses this SIA2BH. It's an abbreviation. This SIA is an abbreviation for sec isoamyl. I have it listed here, so if you remember back the sec group, and that's all the way from the beginning of the semester, along with the T-butyl group and the isobutyl and the isopropyl, and you'll have your sec group as well. So just have that listed here. This will have a boron, we'll have a hydrogen, two of these attached. Again, boron is one of the elements that only has 3 things attached to it, 6 total electrons, and it's stable without its octet. This will react with our alkyne. We're going to add the hydrogen to the more substituted side. So you'll notice we have a R group and a hydrogen. So the hydrogen here added to the more substituted side. So this is anti-Markovnikov addition. In the presence of hydrogen peroxide and sodium hydroxide, we can remove the boron complex and oxidize that to an alcohol. This will go through the base promoted tautomerization to the ketone, and I'll show that mechanism of the tautomerization next. So I'm using hydroxide for the tautomerization here. We're going to deprotonate the hydrogen from our enol. This is our ene part, and here's our alcohol. So once we pull off that proton, we're going to leave oxygen with 1 bond and 3 lone pairs and a negative charge. This will donate down electron density to form a ketone, and then we can resonate this negative charge onto the carbon. So this is resonance stabilized right here with this resonance arrow. We're going to pull off a proton from water and produce hydroxide. So one thing that happened in the acid catalyzed step, if we look back at that for a moment, let me pull that up. Let's see. Here it is. So in the very last step, water picked up a proton and we formed hydronium. You always regenerate your catalyst in the last step. So I wanted to save this while we were talking about both of them side by side. So here we've regenerated our acids. So going back to the base, we regenerate our base in the last step. Just a good rule of thumb to remember. So here's a general reaction, just with everything written out, no mechanism, just this would be like if you had to predict the products, you would be given these two as your reactants, and then you may be given more information saying that it further reacts with hydrogen peroxide and sodium hydroxide. So this ultimately gives us our ketone. You're going to notice something different about this from our last reaction. This will produce an aldehyde. The last type of reaction I'd like to go through in this chapter of discussion of alkynes is a permanganate oxidation. This will use an alkyne. We can use a terminal alkyne, potassium permanganate water, and neutral pH. This will give this really unique compound that has 4 alcohols. So we have 2 vicinal arrangements of these 4 alcohols. We'll lose 2 equivalences of water and we'll form a diketone. So we have 2 side-by-side ketones. Here's an example reaction of that. So you'll notice that the presence of where we have our alkyne, you're going to get that converted to a diketone. One thing that will happen with this is if you don't have an internal alkyne, if you have a terminal alkyne, so if you have at the end of a molecule with that acidic proton that would form that acetylide ion in the presence of sodium amide, just to get your mind thinking of that again, this will form the diketone, but we'll get, I guess, a keto acid instead of a diketone because it goes through this keto-aldehyde structure. The aldehyde is not very stable, and that'll further oxidize to the carboxylic acid shown here. So that's the end of part 2. I hope you found this information useful. Stay tuned for more videos. Thank you.